In the last video, we calculated a confidence interval for a proportion. So we took a sample proportion, then we added a margin of error based on our sample size and our confidence level. So we kind of glossed over this idea of the critical value, which is determined by our confidence level. So we said that for 95% confidence, which is what we were asked for in that problem, we'd use a z-score of 1.96. So I want to talk a little bit about where that number comes from again, and then talk about a slightly different score we're going to use when we deal with sample means. So essentially when I'm looking for that critical value, I'm trying to figure out what z-score do we need to capture that percent of the data. So if for a 95% confidence level, we're trying to capture 95% of the possible samples. So if we want to capture that middle 95% of the data, that's going to leave 5% for the tails, which means on the left tail, we've got 2.5%. Same thing on the right tail, 2.5% over here as well. Now, if I want to know what is the z, what value right here would cut us off to give us that middle 95%, there's some z-score that'll do that. I can use my calculator, or you can use table A for this. I like using the calculator. It's a little bit easier. Go to distributions and go to inverse norm. And remember, inverse norm tells you what area of the curve is to the left of that value. So I'm going to put in 0.025. Or if I wanted, I could put in 0.975 and find that value. We'll get the same number, just the positive version. And that's how we got 1.96. Okay, you can see this is negative 1.96, this is positive 1.96. That makes sense. Our empirical rule tells us 95% of the data is within 2 standard deviations, so should be close to 2. Now, when we deal with a sample mean instead of a sample proportion, we're going to use a slightly different formula. So the key difference is we're using a different statistic. Now we're using the mean of the sample instead of the proportion of the sample. And then we'll have a different formula for the standard error. Looks like this. Standard deviation divided by sample size, the square root of the sample size. We're also going to have a different critical score. So we're going to use, instead of z, we're going to use a t-score. So this doesn't come from the distribution of z's, it comes from the distribution of t's, which is a slightly different distribution, which is better at capturing the variability that we see in sample means. It's really important that we don't get these mixed up. So remember ZAPTAX. It's a good rule of thumb for working with a proportion. So looking at a sample proportion, a p-hat, we're going to use the z-score. If we're working with a mean, x-bar, then we'll use our t-distribution instead. So what is a t-distribution? Well, it's kind of like a normal distribution, and it's going to be similar in a lot of ways. It might look something like this. Okay, so it's supposed to have pretty much the same sort of shape as a normal distribution. It's still kind of that bell shape, or it's supposed to be, but there are some distinct differences. You'll notice that there's a lot more area underneath the tails. In other words, there's a lot more data on the sort of outsides of our distribution. Remember, the height of our density curve represents the amount of data there. So compared to the normal distribution, just very little data outside of 2 standard deviations, the t-distribution is going to have quite a bit more data on the outside. There's more variability. And the other thing about a t-distribution is there are many t-distributions. There's not just a single one. So this might be a t-distribution with a certain degree of freedom, maybe a degree of freedom of 20. This idea of the degrees of freedom is based on our sample size. We just take our sample size and subtract 1 to get our degrees of freedom. And it's a parameter that helps determine how much variability there is in our t-distribution. If we had a really small sample, we might see a t-distribution, and I'm exaggerating a little bit, we might see a t-distribution like this, where there's a lot more variability because we have such a small sample. So this might be a t-distribution with degrees of freedom of 5 or something like that, right? Really small sample size. So if we are trying to figure out what our t-score is. Let's say we want to do 95% confidence. And we also need to talk about the sample size when worrying about AT distributions. Let's say our sample size is 20. So we have, or let's go 30. So we have a sample size of 30 and we want 95% confidence. So I'm going to kind of put this sketch on here to give us a visual. But again, it's the same idea as the z-score. We're going to look at where is the 95% of the data. Okay, so it's going to be a little bit further out probably. And we want to figure out what t-score. Again, I'm just doing this on top of this graph to make it easy, but we're not talking about z-scores anymore, we're talking about t's. So there's some t value that would give us 95% of the data. The way to calculate this is really similar to what we did before. Before we used inverse norm, now we're going to use inverse t. It's the next option in your menu. So we want a 95% confidence. So again, that's an area of 2.5% over here on the edge. And then we need to put in our degrees of freedom. Remember, degrees of freedom is just one less than your sample size. So if our sample size is 30, we're going to have a degrees of freedom of 29. Cool. And you can see it's a little bit different than our z-score. You can see it's just a little bit off, a little more than 2 instead of a little less than 2. But anyway, that's how we get our t-score. So next we're going to actually do an example problem, and you'll see me do the same thing once I have to find my critical value. So now let's take a look at an example problem where we want to calculate a confidence interval for the mean of a certain population. So it's going to be really similar to the last video where we did a proportion confidence interval, but there are a few really important distinctions. We're going to have a slightly different condition that we check. We're going to use a different critical score, t instead of z. Remember, Zaptax. Okay, since we're working on sample mean, we're going to use a t-score. And lastly, the formula is going to be a little bit different. Okay, so it says an environmental group conducted a study to determine whether crows in a region were ingesting food with too much lead in it. Biologists classified lead levels greater than 6 parts per million as unhealthy. The lead levels of a random sample of 23 crows in the region were measured and recorded. The data shown in the stem plot below. Okay, so we got our sample size of 23. It's a random sample, that's good. Cool. Then we have our data here. So part A says, what proportion of crows in the sample had lead levels that are classified as unhealthy? Well, they said more than 6 is unhealthy, and we just need to figure out how many of these were more than 6. So 6.6, 6.8, 6.3, 6.4. So our proportion is 4 out of the 23. Okay, so that's a really simple question. I think they just put this question in here to confuse you because the next question is going to start asking you about the mean. So even though we did just calculate a sample proportion for part A, we're not going to be doing a confidence interval for proportions. We're actually going to be doing it for sample means. Okay, part B says the mean lead level of these 23 crows was 4.9. You could probably check that with all of these numbers if you want to. Standard deviation was 1.12. Again in parts per million. So let's see if we can create a confidence interval here, 95% confidence of what the true mean lead level of these crows is. Okay, so before we get started, let's pick out our statistics here. So first of all, we have a sample mean. So that is x bar equals to 4.90 parts per million. Be careful with your symbols here. You don't want to use mu here. Right? Mu would indicate we're talking about the true mean, right? The actual mean. But we just know the mean that we got in this sample, which should be close, but we'll see how close. Next, we have the standard deviation. And again, this is the standard deviation of this sample. So not sigma, the true standard deviation, but S, or you can call it S sub x, S of x. So the standard deviation of the sample. Okay. So before we calculate a confidence interval, we want to check our 3 conditions. So condition number 1. And I'm going to go ahead and say conditions. So we can only calculate a confidence interval if a certain number of conditions are met. So condition number one is sorry, I lost my train of thought. This is a random sample, right? So I forgot what I was going to say. The sample is randomly selected. So this random condition is really important to check because it tells us that the sample will be representative of the population. So the sample's randomly selected, so it represents the greater population. And maybe you should write that down, but I'm going to save some time. Next, we're going to check for independence. And often we don't actually meet this condition. It's not typical to have independence when we take a true sample, right? We're not going to measure the lead in a crow and then put it back in and then take the same crow again and test it again. We don't usually sample with replacement. So instead, we can meet the 10% condition. And again, this tells us that our sample is 10% or less of the total population. And this is sort of a placeholder for independence. As long as we don't have a huge part of the true population, the calculations are going to be close enough. So 10% condition is met, assuming there are, sorry about my handwriting, more than 230 crows in the region. Again, our sample's 23, so I just multiplied that times 10 to get 230. And finally, we need to check our large sample condition. So the central limit theorem says that the sampling distribution will be approximately normal as long as our sample size is bigger than 30. But it's not. We have a sample size of 23. So this may come up where we don't actually have a big enough sample. So we don't get the easy answer of just we have a big sample so we can just assume the sampling distribution is normal and move on with our lives. But we saw that when we actually looked at the sampling distributions of sample means, of X bars, we saw that if the population started out pretty normal, then we actually didn't need to meet this condition. The sampling distribution would be normal even with really small samples. So what we're going to do here is we're going to say, although our sample size I'm going to say this is not, sorry, I'm going to say this is bigger than 30. It's not bigger than 30. So although our sample size is not large enough to assume the sampling distribution is normal, just actually look at the data. And if we're looking at this data, it's hard to say it's exactly normal, but it is symmetric. We have much more data in the center than we do on the tails. This data looks like it could have been drawn from a normal distribution pretty easily, right? We can imagine that this is fairly normal, or was drawn from a fairly normal population. So we're just going to say that. So although our sample size is not large enough to assume the sampling distribution is normal, our sample looks like it could be drawn. We could say our sample is not skewed, right? Our sample looks pretty symmetric. Looks like it could easily have come from a normal distribution. Okay, so kind of weird condition check on this one. If we just have a large enough sample, which hopefully most of the time we'll have a sample size bigger than 30, but we can still get away with doing our confidence interval as long as the data looks like it could have come from a normal distribution. Okay, so now we're ready to actually do our calculations. So we need to take our statistic plus or minus our critical score. In this case, we're actually using a t-score, and then times our standard error of the statistic. That's going to be s sub x over the square root of n. So this is your formula. On your formula chart, it will say this in words. It'll say the confidence interval is the statistic plus or minus critical value times standard error of the statistic. And you have to remember that if we're working with x bar, our critical value is going to be the t. If we're working with proportion, critical value is the z. So remember, zap tags. And then the formulas for standard error of a statistic is on the formula chart. So you can find this part on the formula chart. Okay, so we can start plugging stuff in. 4.9 plus or minus, wait, what's my t-score? Okay, so what's our t-value? Again, we're looking for 95% confidence, and I'm just doing a quick sketch to help me think about this. We want 95% of the data in the middle, which means we have 2.5% on each chunk. So what I'm going to do is I'm going to go to my calculator, and you could also use the table. Make sure you're using the t table, not the normal table. I'm going to use inverse t. My area is 0.025, right? Because I'm looking for this value that cuts off 2.5% of the data. And I also have to put it in my degrees of freedom. So this is a new concept for us. Degrees of freedom is just one less than the sample size. So our sample size was 23 crows. So our degrees of freedom is 22. So again, degrees of freedom is just one less than the sample size. And we'll get our critical value there. That's a 4. And then we'll do our standard deviation of the sample. It's 1.12 divided by the root of the sample size. Cool. So we can plug that all in and calculate this out. I also want to show you that we can do this in the whole thing in the calculator. And that way you don't actually have to calculate your t-score if you're using the calculator to do all the work for you. So if I press stat and go over to the test menu and look down here, we'll find a t interval. So t interval is what we're looking for. You can actually put in all the data if you wanted to, which would be kind of cool, but we already have the statistics summarized for us, so we're going to put in that. Okay, so our mean is 4.9. Our standard deviation of our sample is 1.12. Sample size is 23. And we want a 0.95, 95% confidence level. Okay, takes noticeably longer to do the t interval. I'm going to round that up. 5.384. Okay, so our confidence interval is going to be between 4.4 parts per million and 5.4-ish parts per million. Cool. All right, so we could have calculated that out here by hand, but these tools in the calculator are so useful and so quick that it'd be a shame not to use them. All right, so lastly, we want to interpret this confidence interval. So what is this telling us? We are 95% confident that the true value, the true mean of lead in crows of this region. What did they say? Crows in the region. We're 95% confident that the true mean of lead in these crows, so crows in the region, these crows, is in the interval from 4.416 parts per million to 5.384 parts per million. Okay, so there's our final answer. We got there eventually, but let's take a look back at all the things we had to do to get there. So first of all, we have to check our conditions before we start a confidence interval, and we're always checking these same three things. Is the sample random? Is the sample independent? And usually not, but we can get away with it if we have the 10% condition met, our sample size less than 10% of the population. We also want to check that our sample is big enough that we can just assume the sampling distribution's normal-ish. And we actually didn't meet that here, but we could take a look at the data and see that it wasn't super skewed left or skewed right or obviously bimodal or anything. Nothing weird's happening. We have pretty symmetric, simple data, so it's reasonable to assume that our population is normal. Cool, so we are making an assumption here that the population is pretty normal since we do have small sample size, but that's okay. And since we could see the sample, I think it's safe to make that assumption. So once we do that, we can go ahead and take a look at the formula. And personally, I like writing down the formula and then starting to plug stuff in and then using the calculator. You can get away with not doing this. You could leave this part off as long as you identified what you were doing. So if you said a one sample mean t interval, you could do that instead of writing down the formula, but I think this is the best way to do it. And finally, we let the calculator help us out to find that, and we wrote a quick sentence.